All right, today we are going to talk about other categories of simple organic molecules. So last time we talked about saturated hydrocarbons, also known as alkanes. Right, just remember, quick refresher, I'll zoom back here at the beginning of the notes. Alkanes, the reason why they're called saturated is because they have the maximum number of hydrogen atoms bonded. In other words, on the carbon chain, wherever carbon can have a bond with hydrogen, it will have a bond with hydrogen. That's what it means to be saturated. However many carbons there are, there's going to be enough hydrogens to fill up all the bonding sites. Okay, so today we're talking about unsaturated hydrocarbons. And let me see if I can make this bigger. Oh, let's do this. Okay, that really wasn't much bigger. All right, anyways. Unsaturated hydrocarbons. The reason why a carbon chain would be unsaturated is because it has a double bond. There's a double bond somewhere. So if there's a double bond somewhere, then some of the bonding locations are reduced, are not present anymore. All right, so compare C2H6, which is an alkane, which by now you should know this as ethane, 2 carbons, right? Versus C2H4. Now C2H4 only has 4 hydrogens, and the reason is because carbon is involved in a double bond. So the first one would be saturated, the second one would be unsaturated. So because they have a formula, because they have the pattern of having a double bond, the formula is simply CnH2n. Remember, the formula for the alkane was CnH2n plus 2, whereas here it's CnH2n. So in other words, they're not adding an additional 2 because 2 locations are compromised and now don't have the ability to make those last 2 bonds with hydrogen. So you have 2 fewer hydrogens in the formula. So to sketch structural formulas for these guys, well, I just did C2H4. Let's do C3H6. So there's 3 carbons. There's 6 hydrogens. Now the thing is, the double bond, I can decide left or right. For right now, I'm just going to say, let's just say that's right over there. Okay. Now notice this carbon here in the middle. Notice that it only has 1 hydrogen on it. And that's because every carbon can only have 4 bonds, right? And the carbon is already involved in a double bond on one side and a single bond with carbon on the other side. There's only 1 bond remaining for hydrogen to be at. Likewise, the first carbon only has 2 hydrogens because it has 2 of its bonds tied up in a double bond with carbon. Every carbon can only have 4 bonds. All right, so as far as naming alkenes, I'm going to make a line here just to kind of get some separation. As far as naming alkenes, we still use the prefix system, and we still use, when we use the suffix of "ene." So therefore, this would be named as propene, because the pro is the prefix for 3 carbons, and it's an "ene." Now, technically, this could be called 1-propene. And the reason why we say 1 is because the double bond, the convention is to have the double bond as close to the end carbon as possible. Right? So 1-propene, or oftentimes it's N-propene. Or you can just say propene. Now, if I redrew this molecule with the double bond on the other side, it wouldn't change the name because we would just count the carbons backwards. Like if we drew this, right? That in pink would still be propene. It's just that I would count this carbon as carbon 1, and this is 2, and this is 3. Now, if there are more carbons and multiple places to put the double bond, then we need to be more specific. So let's say we saw something like this. Okay, so that's 4 carbons long, and I have to assign a number because the number tells you where the double bond is initiated, where it starts. So this would be 2-butene. Do you guys understand why it just can't be called butene? Because butene, without any kind of descriptor, would be shown as this. That's butene, because the 1 is assumed if you don't put a number. Yeah, Ron.
There are side chains. Do anything change?
Yes. If there are chains attached to an alkene, then you still have to put the numbering of carbons into effect. But in terms of prioritizing, the double bond gets priority for the low carbon number. Okay, so like if I were to put a branch on here, like that, this would be called 3-methyl-1-butene. Does that make sense, guys? The double bond must have the lowest carbon number. The branch then is second priority. You know what? I'm going to add a page in here somewhere so we can do a little bit of practice with that. Sorry, the page break is a little awkward. Okay, so let's try a couple. So I'm gonna. So first off the bat, when you look at this, how would you name this? There's 6 carbons, so it's a hexene, and the double bond is on carbon 2. Right? Of course, you wouldn't have if we numbered it the other way. 1, 2, 3, 4, 5, 6. It would be silly to have the double bond start at carbon 4. Okay. Here's the thing. When you have a double bond, what you have to understand, what you have to remember about carbon is that carbon is sp3 hybridized. All right, so it's got angles of 109.5. Now every bond can rotate, but when you have a double bond that's non-terminal, non-terminal means not at the end. So write that down here. Terminal at end, non-terminal elsewhere. Like it could be in the middle, could be close to the end, but the point is terminal is the one at the end. This double bond is non-terminal. Does everybody understand? When you have a double bond that is non-terminal, what that does is it creates 2 isomers. Let's define the term. Oh, we defined the term isomer before last time, didn't we? Isomer, I'll write it again. Isomer is when you have the same formula but different bonding structure, different bonding arrangement. Okay, so what I mean is this. This molecule actually has 2 variations. You see, when you have a double bond, remember how we don't write in all the hydrogens, we just assume the hydrogens are there? Okay, but for the purposes of this particular demonstration, I'm going to draw in the double bonds. or drawing the hydrogens. Okay. This right here, the double bond is locked in place. Whenever you have a double bond, that double bond, the atoms bonded cannot rotate. Think of it as like a brace, right? You know, you put a brace on your leg so you can't bend it when you have a broken leg, right, or a cast. So double bonds prevent rotation. And because of that, this, and the highlighted yellow, that particular series of bonding angles is fixed. Now, because you have the sort of like a crossroads here, like how you can go here, but the other possibility is for this to go upward. And so that is the second isomer. And that looks like this. Yes?
Could that shape also be like inverted, so it's like a trapezoid going that way?
Inverted, just if I flip it upside down, you mean?
Yeah.
Yeah. These in, yes, so like whenever you rotate something, like imagine rotating it, flipping it 180 degrees or 90 degrees, it does not change what it is.
Oh.
Okay. So because you have a double bond, the double bond fixes a certain number of the bonding angles in place. That allows for these two different forms to exist. These are different isomers. Now, imagine taking if we wrote this molecule in the middle of a piece of paper, and then you folded that piece of paper. If I said, all right, does the carbon chain fold inward on the same side, or does the carbon chain extend across the fold to the other side of paper? This changes our naming convention. So when the carbon crosses over, like this first one in yellow, this is the trans isomer, right? And so the name of this would be trans 2-hexene. Because remember, the double bond starts with carbon 2, but because the molecule is crosses over to the opposite side of the double bond, that's trans. And in this second example, this is what we call the cis isomer. So this is cis 2-hexene. Because the carbon chain bends backwards onto the same side. And plus, it kind of also looks like a C. Maybe. Can you see that? It's like a C. If the first part of the chain were longer, Amazon, leave me alone. Okay. Whenever you have a double bond, and the double bond is not at the end, this allows for different possibilities, and you must be aware of it. Okay? If the double bond is on the first carbon, then it doesn't matter. Then this doesn't happen. Because if it's on the first carbon, you have no extension of the carbon before the first carbon. All right? So make sure that it's non-terminal, and then this will happen. Okay. Let's go back. Oh, yeah. So the formula, what would the formula be? The formula for both of these would be C6H12. So giving just a formula is not giving enough information sometimes, right? Hence the other naming conventions, all right? With organic chemistry, there's a multitude of isomers that exist, and we're going to be exploring more of that today. Okay, back up. Now let's talk about an alkyne. Alkynes are also unsaturated. Unsaturated, yep. Because they have a triple bond somewhere. Somewhere in the carbon chain, there is a triple bond between carbon atoms. Right? So acetylene, C2H2, is two carbons that are triple bond to each other. And then the rest of the bonding positions are hydrogens. So something like this. This would be a pent, and the suffix is -ine, so pentyne, and the triple bond initiates on carbon 2, so this is 2-pentyne. Now, look at the angle here. What is the bond angle for those two carbons that are triple bonded? What is it? 180. If it is 180, there is no bending or folding across the plane of the bond or to the other side. So alkynes do not exhibit cis-trans isomerism. They can't, because it's a straight line across where the triple bond is. So that's not an issue. And like before, the triple bond gets priority for the lower numbered carbon. Now, by the way, an alkyne is when there's one triple bond. Just like with alkenes, there's one double bond. Because the question often arises, what if you have more than one double bond or more than one triple bond? That's a different category. All right. If it has more than one double bond, let's say something had two double bonds, that would be called a diene. All right. And then if it had more than one triple bond, it'd be called a diene. Or diene because chemistry is so funny. Okay. Yes.
I assume for alkynes, the same convention protocols, the triple bond would take priority instead of the branches.
Yes. If there's a branch, then the triple bond gets the lower number of carbon first, and then deal with the branch. And then the formula for alkynes, because you have a triple bond, that means you have two less hydrogens than an alkene. So your formula is CnH2n less 2. So what would the chemical formula be for this 2-pentyne that I just drew? N being 5, there's 5 carbons.
So C5H8.
Right, so yeah, 2 times 5 would be 10 less 2, so yeah, C5H8. And let's verify that. Let's see where we can draw hydrogens on here. Well, here you can have 3. And this carbon in the middle, how many hydrogens can we have? None.
0.
Yeah, because it's got 4 bonds on it already. This carbon already has 4 bonds on it. So no hydrogens there. This carbon can have 2, and this carbon can have 3. So yeah, that's 8. You will be asked to draw various organic molecules, and you must remember carbon can only make 4 bonds. I don't want to see any super crazy molecules that look like this. You're breaking the laws of chemistry by doing that. Right? Only 4 bonds. Those hydrogens, not there. Okay? All right. Since we're here, let's do an example of an alkyne. So, what would this be? identify the long chain first, right? Always, that's your first step. Would my long chain start from the left and branch towards the top, branch straight across from left to right, or branch and then go down? Like, in other words, is it this one? Oh, this one, straight across, or this one going down?
They're all the same.
They doesn't matter. They're all the same. So my straight chain is what? What's the parent chain called? There's a triple bond, so we use it with a alkyne suffix. Oct, because there's 8 carbons in the parent chain. I have 2 branches. Here, here. What do we call those? Arms? What are they?
It's on carbon 5, so we, or sorry, I think carbon 6, it would be 6 diethyl.
Yes, the chains are ethyls. There's 2 of them. So this is a diethyl, and they're on carbon 6, but there's two branches, so you need a number for each branch. 6,6-diethyl octane.
Would you put 3 octane in there?
I'm sorry, yes. Ooh, yes, forgot that. And we have to 3 octane. Okay, so the nice thing about naming organics is that they follow the same conventions, pretty much. Same prefixes, branching structure, names for branches are kind of the same. The only thing you got to remember is what takes priority, right? Is it the branch? Is it the double bond or the triple bond? Okay. All right. Now, an aromatic hydrocarbon. An aromatic hydrocarbon are derived from what we call from a structure of benzene. All right, so benzene is a unique structure. If you look at this guy right here, you see 3 triple bonds. You see it also is enclosed. Whenever something is enclosed, it's a cyclo. It means the chain connects to itself, or it's a ring, right? So this is cyclo, and so I should probably talk about cycloalkane first, then we'll talk about benzene. So let's talk about cycloalkanes first. Your general formula for a cycloalkane is CnH2n. And if you think about it, that makes sense, because if you took a carbon chain and you just kind of wrapped it around and connected the ends, you would lose the hydrogens at the ends. So it's an alkane, but you lost 2 hydrogens, so the formula is the same thing as an alkene, right? CnH2n. So 6 carbons connected would actually look like this. And this is what we would call cyclohexane. Does that nomenclature make sense? Only single bonds between carbons, that's why it's an ane. Cyclo because it connects end to end. And hex because there's 6 carbons. So what would this be called? Agreed? Yeah, right. Cyclopropane. Okay. So these are what we call cycloalkanes. They're pretty straightforward. They can have branches. So if I had something like this, so it's a cyclobutane. The branch is 2 carbons long, so this would be ethyl cyclobutane. butane. And branching, the branch must get the lowest carbon number. So we're just going to call this first carbon here carbon number 1. And then which one is carbon number 2? In this case, does not matter. If I go to left, counterclockwise, or go clockwise, it doesn't matter because the branch we've decided is on carbon 1. So technically, this is 1-ethyl cyclobutane, but the 1 can be omitted. Okay. So back up to this benzene character. The cyclobenzene, or I'm sorry, the benzene with 3 triple bonds, this is a pretty important molecule because this is just very, 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 very commonly used as a primer in organic chemistry reactions, right? We attach lots of things to this to make other things. So it's a building block. This is like your basic Lego, okay? Now, benzene is often written like this. Because it's got 3 double bonds, this molecule does exhibit resonance. And so rather than draw this with a double arrow all the time, organic chemists just draw this. That circle implies that the double bond is averaged between all positions, and this is the fastest way to do that, especially when you're sketching out lots of reactions and lots of reactants and products. So you'll see this on the test, and you'll be like, what is that, a weird stop sign? Actually, a stop sign has 8 sides, not 6. But anyways, that's benzene. Okay? All right. We need to go over this quickly. Actually, we don't have time to go over this now. All right, we're going to stop here today because we need to do our lab.